All right, question 2, the diene addition question. Now, if you've looked at the table of contents for your textbook, you know dienes are not one of the things we've covered yet. So, how do I get off asking that question? Because all it is an alkene addition plus resonance. That's things we have covered, so it's not an unfair question. It's a question that you'll see a lot more of with a lot more context in the next course. But it's just an alkene addition question where there's a possibility of resonance. So, here we go. And we have our HCl. First step, attack the hydrogen. Form a cation. Now, that can go one of two ways. Either it gets directly attacked by the chloride, one of the products, or, I'll redraw it so we don't have overlapping arrows, or we have resonance. If we had resonance, we end up with a cation on the end. Now, normally we say a primary cation is a bad thing, but not when it's in conjugation, not when it's part of resonance. A primary cation there is just fine. So, here we are. We attack that one, and that's the other product that we showed on the first page. It's possible to get another stereoisomer here. I kind of ignored that. I kind of avoided that because I didn't want us to get bogged down on irrelevant stuff. So, mechanistically, this is how you get each of them, starting from the same protonation on the far end. So the hydrogen that's been added is here on this carbon all the way through. It's still there, it's still there, it's still there all along. So that has not changed. It hasn't gone anywhere. It hasn't gone anywhere different. The only thing that's changed is where the cation ended up and what happened to it along the road. So, now, the question that kind of hurt people a lot was, which one is better off? And in reality, it's a bit of a trick question. Not a trick question, but it's one that's condition dependent. And you have no reason to know that, which means I basically would have accepted either answer about what I'm about to give you, even though only one of them would be correct depending on the conditions you're talking about. So, at lower temperatures, we have less energy, we're more problematic, our problem is that of activation energy. Resonance is fairly simple, but it still requires an extra movement of a pair of electrons. It still requires alignment of orbitals, so it still requires a little bit of energy because of entropy. So, if I'm just talking the lazy way out, this would be preferable. It's easier. What we call kinetic controlled, or the kinetically favored product, meaning it's just easier to do. It's faster. But if we have more energy in the system, meaning we're at a higher temperature, then we stop worrying about that and we start looking for what's more stable. And it turns out the cation is not the defining issue here. The defining issue stability-wise is the alkene. This is a more substituted alkene than this one. So this is overall more stable. So depending on the energy conditions of the system, we may get one preferably to the other. The overall more stable one is the internal double bond because it's more substituted, more hyperconjugation in the antibonding pi orbital. But depending on the conditions, we may be just saying, okay, the easy cation, which also happens to be secondary versus primary, that doesn't make much of a difference with resonance present, but that's the other explanation for what is preferred at low energy or lower temperatures. So I took either one of those as correct because I didn't give you conditions, nor do I expect you to know that yet. We haven't covered that yet. But I want you to think about it and see what you would come up with. And you came up with reasonable explanations because you do know the answer, depending on which piece you thought was important, either the cation or the overall alkene. So I had some people give me one answer or the other, and reality is either of those could be preferred, but it depends on the actual conditions the reaction was run under, what temperature it is.